Today's going to be a good day because we're making tetrazene. Tetrazene, also known as 1,5-tetrazoyl 3-guanyl tetrazene hydrate, is a compound containing 2 carbon atoms, 6 hydrogens, and 10 nitrogens with a water attached. Now, it's a compound that I have desperately tried to make over the years and failed miserably many times over probably about a 3-year span. I've tried making aminoguanidine bicarbonate, which, yeah, did work, and I do have a small amount of tetrazene.
Yay!
To prove that, it did work, but it's really bad tetrazene, if I'm going to be completely honest. It only works sort of. Some interesting things about tetrazene, besides, its structure and the high amount of nitrogen it has for, its molecular size, is that when it's pressed enough, when the solid crystalline tetrazene is pressed enough, it loses all energetic properties, which is what I believe is called dead pressing. Before we begin, I suggest that you have goggles and gloves, because this synthesis does involve, some corrosive acids and irritating materials. The synthesis of tetrazene involves the reaction of aminoguanidine in solution with sodium nitrite and acetic acid to form the tetrazene hydrate. So that's exactly what I'm going to do today. And ignoring with how filthy my hot plate is, let's get started. All reagents were purchased online, said chemicals being glacial acetic acid, aminoguanidine bicarbonate, and sodium nitrite. The weights of these compounds that we're going to need in the synthesis are 34 grams of aminoguanidine bicarbonate. Here I have 100. We are also going to need 15.7 grams of glacial acetic acid. And finally, 27.6 grams of sodium nitrite. Alright, let's get started. Alright, starting out with aminoguanidine bicarbonate. I'm going to go ahead and weigh it out in this porcelain dish right here. It's a little bit discolored, but it's nothing really that will impact our synthesis. It's just discoloration. So, like the synthesis said, we're going to need 34 grams of aminoguanidine bicarbonate. As we can see, aminoguanidine bicarbonate is a fine white solid. The consistency similar to that of powdered sugar or confectioner's sugar. This aminoguanidine bicarbonate has a lot of volume to it. It's a very fine powder. It's really not that dense. So I've only got about half of what I need right here. So I'm going to go ahead and put this off to the side and keep weighing. Here's all the aminoguanidine bicarbonate. Now, I know it looks like a lot, and, frankly, I don't blame you. But, remember, this is only 34 grams of aminoguanidine bicarbonate. The stuff I got was really nice and light and fluffy. As you can see, it looks exactly like powdered sugar, but, don't put this on your donuts. Alright, I'm going to go ahead and set this off to the side and start weighing out the next chemical. Okay. What we're going to need next is 15.7 grams of glacial acetic acid. Glacial acetic acid is basically any acetic acid, with a concentration near or above 99%. So I'm going to go ahead and weigh out 15.7 grams and come back when that's done. Okay, so here I have 15.71 grams of glacial acetic acid, which corresponds to about 18 or 19 milliliters. So that's pretty good. I'm going to go ahead and set that off to the side and weigh out our final ingredient. The last thing we're going to need is sodium nitrite. Sodium nitrite is a pale yellow crystalline solid with the formula NaNO2 and is used in meat curing, if I'm correct. So we're going to need, I believe, 27.6 grams of this. So I'm going to go ahead and add that to this cleaned out crucible right here. And I'm going to go ahead and skip to when that's done. And so the final reagent is weighed out. Now that we have everything weighed out, we can go ahead and set the sodium nitrite off to the side for a while, since we don't need that for a while, and go ahead and prepare our beakers. This synthesis calls for a 3-liter flask with over, 2,500, like 2.5 liters of water. I think that's a bit liberal for the synthesis, since I have done it before, and it works just fine with less water. So what I'm going to go ahead and do is get a 1-liter beaker, and we can go ahead and add probably I'd say 700 milliliters of water is probably good for the synthesis. With all that water added, we can go ahead and add a stir bar of your choice. I'm going to go ahead and use a flat-ended one because I usually use that for best stirring, because there's going to be some gas involved if you didn't guess. Anyway, I'm just going to grab my excess distilled water in a little squirty thing here. And I'm going to go ahead and add our glacial acetic acid. And turn on the stirring first. We're just going to dissolve the glacial acetic acid. And I'll wash out my beaker with a little distilled water and add that. And I'm going to go ahead and turn up stirring here and make sure everything's mixed. And we can continue on to the next step. Oh, that's pretty loud. Jeez. Now that everything's added, we can go ahead and start to slowly add the aminoguanidine bicarbonate. I shouldn't have to remind you, with of course it being a bicarbonate salt, that it's going to release a lot of CO2. So try to keep the bubbling down, try to keep a slow, steady addition of the bicarbonate, because this is basically like adding a carbonate to vinegar. This is probably a little bit stronger than vinegar, but you get the point. And in goes the bicarbonate. Aminoguanidine bicarbonate, that is. Now what this is doing is it's releasing CO2 and forming the salt aminoguanidine acetate, which is water soluble. And that's going to be able to react with the sodium nitrite to form our final product, tetrazene. So once this is all added and all the CO2 has died down, I'll come back and we'll continue on with the synthesis. Okay, now all the aminoguanidine bicarbonate is in this mixture. So what I'm going to do now to convert it all to the acetate is both heat and stir for... Gosh, no, I'm not sure. I'll put it up on the screen, but I have no idea. Just until the solution goes pretty much clear. Now, of course, not everything went into solution, but that's alright. So what I'm going to do now is filter it and let it cool to 30 degrees Celsius. Then we can go ahead and proceed on to the next step. Now what we can do is add our solution of aminoguanidine acetate back into the beaker. This beaker is cleaned. So you can see we have about 800 milliliters. And what I'm going to want to do now, after washing out the filter flask with a small amount of distilled water, I'm just going to add that, is we're going to let this cool down to 30 degrees C and then add all of the solid sodium nitrite. I'll come back when I'm ready to do that. Okay, now that it's at about 30 degrees, right now it's 33.1 degrees Fahrenheit, Celsius. Was I really about to say Fahrenheit? Oh, man. Imperial System scrub right here, I'm sorry. Yeah, 33.1 degrees Celsius, but it's close enough to 30 degrees. So, I'm going to go ahead and all at once just dump in the sodium nitrite as a solid. Oh boy, it's kind of sticking. Ooh. All at once. There we go. we're going to stir this until it dissolves. Shouldn't take very long. And this is the reaction that forms the tetrazene. When this is all dissolved, I'm going to transfer it into this 1 liter Erlenmeyer right here. And then we can go ahead and wait. I believe it says wait for 2 to 3 hours, or maybe 3 to 4 hours, and then shake the flask around to start the crystallization, and then, you know, let it, at room temperature, of course, and then let it just sort of sit for anywhere between 20 and 24 hours to get complete crystallization of the tetrazene. So, that's what I'm going to do now. I'm just going to transfer it to the Erlenmeyer flask and let it sit, basically, for a while. I'll come back when that's done. Now that's a lot of tetrazene. So here it is, after many years and even more failed attempts. Here's the tetrazene. It's a sort of yellowish powder with a very fluffy consistency. It's nice. I have another batch over there. Actually, not another batch. It was just a second crystallization that just happened to come out. But yeah, so it's a good amount of tetrazene. Still might be a tiny bit wet since it's just so humid where I am at this time of year. But let me go ahead and go down to a safer place to show you how this stuff performs. Alright, so now it's about time to see how this stuff performs. So, what I have here is just a little bit of tetrazene. And I'm going to go ahead and put it on that spoon. And we're going to see what happens when a flame is put to it. As expected, a lot of sort of grayish black smoke and a big poof. Now that's because, as we know, tetrazene has practically no oxygen in it, besides for the water in the hydrate of the molecule, but it has a ton of nitrogen, and that is what gives us that, you know, basically vigorous reaction to these mosquitoes, to when a flame is put to it, or when energy is applied to it. It releases all the energy that is stored basically within all that nitrogen. So pretty cool. Let's go ahead. I'm going to go ahead and show you a few more tests, and then we can go on to possibly some shock tests. Alright, now here's a little more tetrazene, and I'm going to zoom out just a bit more. Very nice. I'm going to go ahead and do that one more time, and then we can move on to the shock tests. Alright, this is the last flame test, and actually what I'm going to do after this is go to a direct heat test. So this is the last flame test of the Tetrazene. Very nice. This stuff's really cool. I love playing with it. It never really detonates, but it creates a lot of smoke, and it's not even that loud. No real flame even. It's a super fun compound, and if you have the right stuff, it's stupid easy to make. Okay, so the last test I have is the heat test, and what I'm going to do is heat up a rod of our old friend tungsten, and go ahead and set that on the Tetrazene. So once I have a propane torch off screen, and I'm just heating up the tungsten rod. Once that's sufficiently hot, yep, I'm going to go ahead and touch it to the Tetrazene. Yeah, and just like I expected, even heat from something that is not a flame, just a hot metal tungsten rod, is enough to set it off. So, now we can go on to the hammer tests, which I might need to get some hearing protection for. Okay, so now I'm outside, and I'm wearing a helmet, face shield, and earmuffs. So, here I have the Tetrazene on a slightly wet rock, and here I have a hammer. I'm just going to smack it till it blows up. Oh, that was quick, I guess. Let me go ahead and try that again. Alrighty, this should give us a little more of a bang. This stuff really isn't all that bad, even for shock sensitivity. I think I damaged the rock more with the hammer than I did with the actual explosive. So, yeah, that's kind of interesting. Let me try a small friction sensitivity. Alright, so for the friction sensitivity, I'm just going to basically scrape it with this hammer. Thinking, man, I don't know what's going on with this stuff. It seems really, really kind of safe. That's a little suspicious to me. I think it might be because of the water, but yeah, whatever. So yeah, this was the synthesis of Tetrazene, also known as 1,5-tetrazollyl 3-guanyl tetrazene hydrate. I really hope you enjoyed. You can subscribe if you want to, like if you want to, and thank you very much for watching. This was an awesome video to make. See you next time.